you may also hear of something called a motional EMF. And basically, what that means is move the loop. In a magnetic field. Right. In all those examples I did at the beginning, in almost all of them, the loop was stationary. We were moving the magnets, we were changing currents, we weren't moving the loop. That very last one where I let the loop drop, that would have been a motional EMF. So let's look at those more carefully. Let's start with a conducting bar, or a metal bar in a B field. So let's see. We would want to think about this piece of metal like this, and a B field like we always draw, in this case, into the board. All over the place, okay? So we want to think about, in motional EMF, you still think about what's called the Lorentz force. The QE force, so F equals QE for the electric field, F equals QV cross B for the magnetic field. So you add those together, that's the total force a charge will feel in any combination of electric and magnetic fields. It's called the Lorentz force. And we have to think about what will that be. So we have charges in here, and since it's a conductor, we have charges that are free to move. Let's keep it real and treat it like a metal. So let's say that the electrons, the negative charges, are free to move. The positive charges are stuck. So we have a bunch of electrons negatively charged, free to move, with a velocity like this. Let's say we let it move to the right. Then those electrons are going to feel a force. V cross B is up, but that would be for the positive charges. The electrons are going to feel a force down, and they're going to all crowd around down here. Okay? So the free electrons respond to B due to F equals M V cross B. And they go to the bottom, which has to leave some of these positive nuclei slightly uncovered up here. So what we've done is we have sort of polarized this rod, and basically electrons move until, I think we sort of did this before, we're creating an electric field here. Okay? Electric field that looks like this inside the material. The electric field makes them want to come together, the magnetic field makes them want to go away, go apart, so it goes until QE equals Q. Yeah, obviously, QVB, if we're just doing magnitudes. Okay. So then what you find is the Q's go away, and you can figure out that the electric field you generate will depend on the magnetic field and how fast you move. Okay? But where's the EMF? There's no EMF. There's no current flow here. This is just a static thing that happens, a static situation. If it's moving with constant velocity, you'll get this separation. It just sits there. There's no current flow. Let me go back to my notes. Ah, yes, I said a loop. I didn't do a loop. I did a bar. Okay, let's do a loop. So magnetic field, boom, boom, in the board. I need to reconnect my magnetic field. So magnetic field in the board. Let's do a loop, and let's do a big, thick loop where you can really see its edges. And let's make that move to the right. And let's think about the QV cross B force on the electrons. So electrons sitting in here, they're free to move. V cross B is up, but they're electrons and they're negative, so they feel a force down. And you get some negative electrons down here, which leaves some positive up here. And what happens over here? V cross B is up, but their electrons, they go down. Negative flows down here, positive up here, negative down here, positive up here. There's no EMF yet. We messed up again. All this is going to do is polarize this object. There's no EMF. And wait a minute, look. There's no d phi b dt. So there better not be an EMF. Okay, let me try one more time. Okay, now I remember. We got to do this. Magnetic field into the board. A uniform magnetic field. We're not going to change that. We could make the field non-uniform, but then we would have to do vector calculus. We don't want to do that. What we need is that bar like that. And then we need it to be on kind of a frame. Uh-oh. Like this. I just ushered myself, here we go, okay. Like this. So this is a stationary frame, and it's like, it's metal, you know, it's a conductor. And this is a sliding bar. Right there. So now only one part of the loop can move. This, we'll say, is the x-axis, like that, and we'll call this the origin when it first, we'll call that 0. It's starting at 0. Okay? Now, what we're going to do is move just this bar. And let's see what happens. Let's think, when this bar moves, its free electrons are going to feel a force. V cross B is up, but they're electrons, so they're going to go down. So these electrons go over here. And that leaves positively uncharged nuclei up there. This has lots of free electrons, and they're happy to move around, but they're not being pushed by anyone because they're not moving. So they say, oh, we'll go over here. Those electrons take off on a journey to go meet these electrons and cover those up, but then they make these, they push these over here, and they go around, and you have a loop. Okay? Or, I'm sorry, then you have an EMF. Current flows around the loop like that because you're constantly pushing your electrons down, but they can constantly go around the loop where there's no force and get back. So we have finally succeeded in making a current. We have made an EMF by only allowing one piece to change. And even better, because we have a change in the flux. Right? Now the area is changing. Magnetic field is constant, but our area is getting bigger. So B dot A is increasing or decreasing depending on which way you call positive. But basically, if this doesn't change, you make an EMF. So with motional EMF, sometimes you can actually analyze it and see it just with the Lorentz force. It doesn't mean that you don't need Faraday's law, that doesn't exist. It just means Faraday's law always works out. And if it's motional, you can get it from the Lorentz force. Okay? So there really is just sort of one Faraday's law. It's just when you do motional, it looks different. But the point is, both laws always work. They both end up being true. Let's analyze it a little bit more carefully. Let's see what phi b is. Phi b, let's see, that's b dot dA, that's the B field times the area. So the B field we'll just say is constant into the board, whatever, its magnitude is B. And the area we'll say is L, which is the length of the rod, or the length between the two rails, times how far it goes here in x. All right? So we could put the origin here and say it's already at x, it already has some area, it doesn't matter. So BLX, okay, let's do that. There you go, it's x, vector, whatever. Okay, so phi b is BLX, and we want to say that the EMF is minus d phi b dt, so the EMF is minus, and the derivative of b and L are constant, so it's minus b LV. So with a combination of Faraday's law and the and just by looking at the geometry, we can figure out how much current, or the EMF induced is BLV, and if we wanted the current induced, we would just need to know the resistance. Yeah, overall. So there you go. Motional EMF is often sort of a combination, or it often requires you to think about the Lorentz force to see it. Another important thing about induction is that without a power supply, induction always damps motion. So let's think about that moving slider like we had last time. I won't draw it quite as nice, but we have a uniform B field into the board, and we'll just draw it as wires this time, like this, and acknowledge that it has some resistance like that. And we'll imagine that this is the x-axis, and the slider can sit right there, like that, just like before. Some resistance R. So now we're going to do a kinematics problem. We're going to give it an initial, the slider, and initial V naught. And see what happens. I probably could have just said that. All right, so the slider is given V naught that way. And by see what happens means let's solve for the velocity as a function of time. Will it slow down? Will it speed up? Will it stay constant? Will it explode? Who knows what it will do? So in this case, we would probably want to think about Faraday's law of induction. EMF is minus d phi b dt. And it's just like last time, it ends up being minus BLV. What I didn't say last time is that we're assuming the area vector is pointing into the board. And then in that way, it makes sense that the area vector is down, is into the board, the B field is into the board, so it has a positive flux. And as we pull, as this moves this way, we have an increasing positive flux. Therefore, the EMF has to come out negative. This is positive. This thing will be negative. And that's why we know that the current goes this way. A positive current would go this way. Our thumb along A, positive would go that way. We know, we worked out and thought about the QV cross B force. We know that the current is going to go this way, which means this bar now has a current in it going that way. So when you give it initial velocity, current flows, just like we talked about last time. The current, I, is the EMF over R, so it's basically minus BLV over R. So there's our current. Now, let's think about the force on the bar. So if we're going to do kinematics, something has to happen other than just this thing moving. It will experience a force because now it's carrying a current and it's in a magnetic field. There's an IL cross B force. So I is this way, L is also this way. If L is the length of the slider, so we can point out that this is L, just like it was a little L before, now it's big L, grew up. It's going to be I, L is this way, cross B is that way. It's going to feel a force this way. Right? It is FB. It will feel a force that way. And you might think we already used that force. We used that force to get the induction. And actually, no, we didn't. Okay? So when we thought about the induction, we said the charges, the free charges in the metal are moving this way. And we said that V cross B caused the polarization, which ends up causing induction. Now we have something different. Not a velocity this way. We have a velocity of charge carriers if they're electrons this way and if they're positive that way. So it's actually at 90 degrees to that other velocity we thought about. It's actually, the electrons are actually kind of moving that way. Right? So now that the current makes them move this way, we apply the QV cross B force again, in this case an ILB version of it, and we say, yeah, actually when you make it move that way, there's more velocity, and now it feels a force moving back, which is equal to ILB. Since everything's at 90 degrees, we just worry about magnitudes. Force on bar is ILB. Now the current is negative, but when we go plugging it in here, that will make it negative. Okay, so you know that the force is in the negative x direction. It should come out negative, but it will. Because this negative value goes in here, the force will come out negative. So that part's okay. Okay, so we have something with initial velocity this way and a force dragging it back that way that depends on its velocity. Oh, that's going to make a mess. Let's do kinematics. Sum of the forces equals ma. So the only force is this ILB force. Let's go ahead and plug in the current into ILB, and it becomes negative BLV over R times LB. So the LBs are squared, and I've gone and used a little L instead of big L, because I was thinking of the last board. So the B's and the L's are squared, so it ends up that the force is minus B squared L squared V over R, minus B squared L squared V over R. And that is the instantaneous velocity, not just the initial velocity. Here is this velocity changes. If it changes due to the kinematics, this will still be the current. That's velocity as a function of time. So if minus BLV over R equals m, and what is A? A is dV dt. Okay? Okay, so now if we solve for, well, we'll try to simplify it. We can solve for dV dt equals, we can bring the m over here, minus B squared L squared over m R V. And you may recognize that as exponential decay. So that's a differential equation. You can't solve it by integration. You can't just integrate this. You can integrate this side with respect to time and get v as a function of time, but you can't integrate that with respect to time because that's the function you're looking for. This is why differential equations are hard. But if you recognize that as exponential decay, then you know that what you're going to get is that v as a function of time is v naught, and then it's going to decay as e to the minus b squared L squared over mRt. So what this means is if we give this thing an initial kick, it'll slow down to 0. At time equals 0, e to the 0 is 1, it'll go at v naught, but then it'll exponentially decay and that initial velocity will be lost. Where's it going? Physically, it's being lost as heat in the resistor. Now, that's the answer. We solved the problem. If you didn't like this, if you want to do that integral, I'm going to do that integral now. If you like that, just stop the video. But just in case, I want to catch everybody, no matter what their math background is. This is one of the few differential equations like this that you can actually do. So it's so exciting, I actually want to do it. So all you got to do in this case is get the v's on one side and the t's on the other. So you say dv over v, brought that v under, take the t to the other side, minus b squared L squared over mR t dt. Right? And now integrate both sides. And you got to think about your problem. We're trying to go from v naught to some v at time t, and v naught happened at 0, and we're trying to get the v at some time t. Okay? So the integral of dv over v, the integral of dx over x, is the natural log of x, or in this case v, evaluated v naught to v. And the integral of that constant times dt is just that constant times t, minus b squared L squared over mR t, evaluated from 0 to t. All right, so if you plug these in, this is natural log of v minus natural log of v naught, but natural logs, when you subtract them, it's really the ratio. So this is the natural log of v over v naught. And this is you plug in t, then you plug in 0. It's just minus b squared L squared over mR t. And then the thing that you like is under the log, and you don't want that to happen, so you exponentiate both sides. So e to the log of something is the something. V, I'm supposed to be saying ln, I forgot, we talked about that. V over v naught equals e to the minus b squared L squared over mR t, and then multiply the v naught, and you get v as a function of time. I'll write it the function of time now, equals v naught e to the minus b squared L squared over mR t. If you take a full E&M class with circuits, you do derivations like that all the time in circuits and understanding circuit behavior. So being able to do those little integrals and similar ones is pretty important in a class like this that would have circuits in it.